All right. Well, hello, everybody. Welcome to this webinar on industrial heat pumps. My name is Doug Herodis. I'm the director of the Upper West On-Site Energy Technical Assistance Partnership. And I'd like to welcome you to this webinar today. Alex, can you go to the next slide, please?
Yes, sir.
All right. If you're not presenting, we've muted your mic for this webinar, and your video should be turned off. We will be recording and transcribing the meeting, and we'll share that out afterwards. At the end of the webinar, we'll have a few minutes where we can enable mics and cameras for questions. However, if you have a question as we go, please enter that into the chat, and we will try to answer questions as we go, if possible. If you weren't aware of this in Teams, you can enable closed captioning. Just click on the ellipses there, and there's an option to turn on live captions. Okay, and with that, we're going, just before the industrial heat pump content, we're going to share a little information on 3 programs that may be helpful to you or to your company. And the first of which will be the DOE On-Site Energy Technical Assistance Partnership. For that, I'll pass it off to Alex.
Well, good morning or midday to everyone. My name is Alex Semino-Hurt, and I'm going to tell you about the On-Site Energy TAP that, of course, is hosting this webinar, and we want to extend a warm welcome to everybody. So you met Doug, and now you get to meet me. I'm the assistant director, and I'm going to just take a few minutes to kind of give you a sense of what the On-Site Energy TAP is and what it can offer you all. So the On-Site Energy TAP was launched just this January, and it was launched really to ask kind of one question that manufacturers and other industrial end users are starting to ask of DOE. And that question is, how can on-site energy technologies help my site meet its goals? There's a lot of these technologies are in the news now, and it's a very rapidly changing environment. So the DOE has launched this program to extend technical assistance to you all to help your site figure that out. And as you can see here, there are 12 different technologies that we investigate, including, of course, industrial heat pumps, which we'll be talking about today. And so if any of these technologies are of interest to your site or some combination of them, we can help you and give you technical assistance. So what does that actually mean? Well, there are 3 pillars to what this program offers. The first and foremost is technical assistance in the form of feasibility studies that we can do for your site to determine, maximally how on-site energy technologies might be able to benefit your site or meet your site's goals of one sort or another. We also do end user engagement, which of course this webinar is an example of, where we'll provide education and other resources to end users so that they can tackle these technologies and understand them better. And then last but not least, of course, is stakeholder engagement. We will reach out to and we work with stakeholders like state energy offices, utilities, and other big partners that help us extend this message. So with that, I'm going to hand it over to Matt DeHaan to talk a little bit about one of the other resources that is available, which is the Industrial Assessment Center and their assessments. This from the Utah Intermountain Industrial Assessment Center. Matt?
Hey, thank you so much, Alex, for turning this time over to me. Yeah, as you said, I'm Matt DeHaan from the IIAC. So the IIACs, or Industrial Assessment Centers, is a program funded also through the DOE, located throughout the nation. There's maybe 20 or 30 of these IACs throughout the US. Here at the University of Utah, we run the IIAC, or the Intermountain Industrial Assessment Center, which services areas in Utah, Idaho, Wyoming, and other surrounding areas. So we can go on to the next slide, and I'll introduce a little bit more about what we do. So some of our goals, we will come out and assess an industrial site, and then there's a 60-day report writing process afterwards. And through all of this, our goal is to reduce expenditures of these industries, by 10%, or their energy expenditures by 10%. This is through recommending typically 4 to 8 recommendations with 2 or hopefully less 2 years of payback. This is all comes at no cost to the end user or to the industry. And we typically look at the big things like boilers, chillers, compressors, the big energy users, and see how we can make those more efficient. So if this is something your site could use, you can fill out an application here at energy.utah.edu, or our programs director is Julie Sieving. Her email's up there on the slide as well. And the last thing that we're really hoping to help people out with, so after we do an assessment at a certain site, we're able to help them through an implementation grant process. Some of the qualifications are listed here on the slide, but what it is it's up to $300,000 of monetary assistance, split at 50-50 cost sharing. So any of these recommendations that we make, industries are able to apply for up to $300,000 of monetary assistance. So there's a lot more I could talk about, but there's the IAC in a nutshell.
Thanks so much, Matt. Really appreciate it. And next, we're going to have John Howlett talk about some of the resources available through Rocky Mountain Power's program, the WattSmart Business Program.
Yeah, thanks, Alex. As Alex said, my name's John Howlett. I'm a project manager for the Rocky Mountain Power Efficiency Program. And for those of you who are Rocky Mountain Power customers, we have a similar program to the IAC program, but it's just for Rocky Mountain Power customers. We have this terrific energy efficiency program called WattSmart. Go on to the next slide. The WattSmart program provides customers with technical assistance to find and analyze efficiency opportunities. And those opportunities can include custom analysis, where, for example, if you're looking at buying a new compressed air system, we can analyze and monitor the existing compressed air system to help you identify what the most optimal new equipment might be to meet the requirements that you have for your existing system. Energy management projects are another type of project that we look at, which are low and no cost projects. An example there might be on your compressed air system. If you lowered your compressed air pressure, that's going to use less energy, and by using less energy, you're saving energy, and there are incentives available for that. And finally, there are some typical measures that we often see that have a prescriptive incentive amount for those. For example, on your compressed air system, if you install a no-loss condensate air drain, those have a fixed amount of incentive that you can get for implementing those. So we'd love to help you identify any of these projects that you could get incentives for through your Rocky Mountain Power utility company, and we're here to help you obtain those incentives, as well as help you identify opportunities. If you don't know what the opportunities might be now, reach out, we can help, and hope you enjoy the rest of the webinar.
Thank you, John. So that's just a taste of a lot of resources that are available to end users looking to improve their operations with their site. And as a quick reminder, with on-site energy, that provides us you an understanding of on-site energy generation technologies. And then, of course, the IAC and the WattSmart business programs can help you with energy efficiency and improving the operation of them. So without further ado, now we can get on back to the main topic for today and talk about industrial heat pumps. And at this point, I'm going to turn it over to Doug to introduce our speakers.
Yeah, thanks, Alex. Well, we're really lucky today to be joined by Regan Cronin and Steve Koski of Cascade Energy. They've put together a great presentation for us today on industrial heat pumps. I've got a little introduction here for each. Regan is a senior engineer at Cascade Energy. She provides technical engineering services for multiple demand-side management programs, including those of Energy Trust of Oregon, Bonneville Power Administration, Pacific Power, and several corporate clients. Regan has extensive industrial process experience. She's familiar with data logging, identifying energy project opportunities, calculating energy savings, and energy modeling. Regan is a registered professional engineer in Oregon. Some of her recent work focuses on industrial heat pump applications in the Pacific Northwest. And Steve is a seasoned technical communicator with over 20 years of experience in industrial energy efficiency. Cascade Energy's technical training lead. He focuses on training and mentoring new engineers. He also serves as Cascade's lead research engineer for industrial heat pumps and investigates other decarbonization technologies. Steve has extensive experience in technical engineering services, particularly in refrigeration, cold storage, and compressed air systems. So thank you for joining us, and welcome Regan and Steve. And with that, I will pass it on to Regan.
Perfect. Thanks, Doug. All right. So as Doug mentioned, we're talking about heat pumps today. On our agenda, we're going to talk a little bit about electrification and kind of why we're talking about that, how it fits into the heat pump world. Heat pumps' role in decarbonization, kind of how they work, where we might apply them, what the market looks like today, and then we're going to wrap up with talking about a couple of the projects we've scoped recently and kind of what the market looks like from our perspective here today. So let's dive right in. We're talking about heat pumps, which is an electric technology, but I think first to really understand why we're talking about heat pumps, we need to understand electrification and how that heat pump technology ties into this concept. So electrification, very simply put, is the shift from the consumption of fossil fuels to the consumption of electricity. So instead of burning natural gas on site, my site might purchase more electricity from the grid to perform the same function. But why are we doing this? Is electricity inherently greener than fossil fuels? Well, the idea is hopefully soon. We're greening the grid right now. We're looking to use less fossil fuels and more renewables to generate electricity for the grid. So as an example, if we're using natural gas at our facility to feed a boiler, to make steam, or in a gas burner to warm the air for any type of office space, we don't have a lot of influence over the CO2 emissions from that natural gas that's burned. Natural gas is methane, and for every 1 molecule of methane we burn, we generate 1 molecule of carbon dioxide. That's just the chemical conversion of that process. And so we don't really have a lot of influence over the emissions from that. Utilities can, on the other hand, utilities can significantly influence the emissions from the power from the grid by changing the resource mix of their grid, of what is generating the electricity. So by bringing on more solar and wind or geothermal or nuclear and moving away from coal and natural gas, we can green our grid and reduce the energy or the carbon intensity of our grid in favor of electric technologies. So how is the US doing in greening our grid? This is emissions by sector over the last 30-ish years reported in carbon dioxide equivalent. And as you can see, electric power generation emissions have been decreasing in the US over the last 20-ish years. So utilities are installing more renewables in alignment with our 100% clean energy goal, which the US has targeted to reach by 2035. So in the US, we're targeting to have 100% clean energy on our grid by 2035, which is about 10 years from now. So we need to start moving on this, and there has been a lot of work by utilities to kind of figure out how this is going to happen. But this is exactly why electrification and electric technologies like heat pumps will start making sense and are starting to make sense today. From an emissions perspective and hopefully a cost perspective, we can reduce the emissions by using this clean electricity from the grid rather than burning fossil fuels directly on site. So one question we're asked right now is, does electrifying today guarantee a reduction in CO2 emissions? And the answer is no, it kind of depends. So the grid or electricity source that you're purchasing that electricity from must be greener than the fossil fuel it's replacing. So if your utility is burning coal to generate your electricity, it might be more, it might be less carbon intensive to burn natural gas on site. So you really have to look at the resource mix of your grid. But hopefully with that 2035 goal of having 100% clean electricity, we're getting there or should be there soon. Okay, so one of the ways that we can take advantage of the green grid and this revolution to renewable energy is to take advantage of electric technologies like heat pumps to decarbonize. So how do heat pumps fit into the decarbonization framework for industry in the United States right now? So in the US, the majority of manufacturing energy is used for process heating. So you see that on the right side of the screen. It accounts for over 50% of the energy use on site at these large industrial and manufacturing facilities, which, if we kind of break that down a little bit further, represents about 9% of the entire emissions footprint in the US. And the vast majority of those emissions are from like fossil gas. And one kind of staggering statistic is about 36% of the heat generated for these process heating applications isn't actually useful heat. So it's 100% wasted, which is really fascinating. So there's a lot of waste that goes in. It's a big chunk of the pie, and then a big chunk of that is actually not even being used. So process heating, as we can see, is a huge portion of that emissions pie and a huge opportunity for electrification if we can transfer that load to the green electric grid or clean electric grid. So electrifying these loads with heat pumps could reduce manufacturing emissions by roughly 1/3, which would reduce the total CO2 emissions total US CO2 emissions by roughly 3%. So there is a lot of opportunity to decarbonize here, and it does make a noticeable impact if we can convert some of these fossil applications to electric. And additionally, heat pumps have another advantage, which they can heat and cool. So it can be useful in providing some facility cooling as well. And we'll talk about that here in a second. Okay, so because we're greening the grid and because heat pumps use electricity instead of fossil fuels to provide heat, heat pumps are one of the many decarbonization solutions that are out there on the market today. And they're just kind of starting to get started here in the US. So there's a lot of potential for these projects. Okay, so quick poll. I think you can just type this into the chat. Which of these industries uses a lot of heat pumps today? Put A, B, or C there in the chat if you'd like. I'll open the chat. B, yeah, I think that's right. Let's see if my animation works. Oh, it doesn't work. Okay, yeah. B, lumber drying. I think pulp and paper is starting to get started on that stuff, but as Steve will talk about later, there's a lot of applications specifically for lumber drying, just because it's such a moist, hot air stream when you're drying lumber that it is a really good application for heat pumps. But we're hoping to see this technology expand into all industries as well. Okay, so we're greening the grid. We're really excited about electric heat pumps. How do they work? How is this technology going to fit in? How can we take advantage of this? Let's talk about the mechanics of a heat pump. So let's talk about how they work. So a heat pump moves heat from one place to another using electric energy. And along the way, it's boosting the temperature of that heat. So we're moving it from either outside or inside or from one process to another. And then we're kind of upgrading and elevating the temperature of that heat so it becomes more useful to us in our application. So in a residential setting, as I think most people are familiar with, if we are cooling our building in the summer, what we want to do is we want to extract heat from our building and move that heat outside, reject it outside to cool our building down. And we're going to extract that energy, move that heat around with electric energy. In the wintertime, if I wanted to heat my building, I'm going to be moving heat from outside with electric energy to the inside of my building, kind of boosting the temperature of that heat to heat my building. So we can heat and cool with heat pumps, and we're just kind of moving that heat around, pulling it from where we don't want it or where we want to extract heat from, and moving it to where we think it's going to be more useful at a higher temperature with electric energy from the grid. So if we dive into this a little bit deeper, how does this work? It's using the refrigeration cycle. So in this example here, I have the mechanical vapor compression cycle. And let's just kind of talk through all the 4 components. So we're going to start at the evaporator, and I'm going to grab my laser pointer. So here at the bottom, we have the evaporator. And here what we're doing is we're absorbing heat from the process or from another process that we need to cool down or from the air. And we're transferring that heat energy, which is my pink stream, into a refrigerant here at my evaporator. And then I'm going to evaporate that refrigerant, it's going to absorb that heat and change phase. And that's the heat that I'm recovering here, the heat in. That refrigerant, the compressor is going to pull on that vaporized refrigerant, and it's going to move that heat that I've recovered using electric power, and it's going to reject that heat that I recovered plus some additional heat that's generated and boost that energy, that heat, up to my condenser here, which is where I'm going to reject that heat out. So in this application, I am probably heating. I probably want to heat something. So this heat energy is going to be the combination of the pink, what I recovered, and what I'm putting in and boosting with my compressor. And then that refrigerant is going to condense here. I'm going to reject that heat to my process or to my airstream into my building. And that refrigerant is going to come back down, come through the expansion valve, flash down to a low temperature, low pressure gas again, and kind of restart the cycle. Okay, so in the industry, let me get rid of my laser pointer. Here we go. In industry, what this process is, or both sides of this process are called, is on the heat recovery side, where I want to extract heat from. This is called the source. Where am I recovering heat? For a lot of residential heat pumps, I mean, for all residential heat pumps that I know of, the source is the air outside. So you have that little unit outside, and you're extracting heat, recovering heat from the air. And then the sink is where you're sending that heat to. So that is like your house or another process that you're heating. Okay, so how are heat pumps rated? To rate the performance of heat pumps, the industry uses a term called the coefficient of performance. And the coefficient of performance is a ratio, a unitless number that's the ratio of the amount of heat energy out for the amount of electric energy in similar units. So it's the ratio of how much heat am I getting out, how much I'm spending to kind of recover that heat and move and boost that heat. So in this example, if we just wanted to calculate the COP of this heat pump, in this example, I'm recovering 30 units of heat energy from my source. I'm spending 10 units of energy to move and boost that heat, and I'm getting 40 units of heat out. So the COP in this case would be 40 over 10, and it would be 4. If we compare the COP and efficiency of a heat pump to like a fuel boiler or a burner, in this case, if I'm spending, if I'm still getting 40 units of heat energy out, I might have to spend about 50 units of fuel energy in to get that same amount of heat out. And in this case, the COP is 40 over 50, which is 80%. So the COP is the same thing as saying efficiency, but a lot of engineers are very uncomfortable with having an efficiency over 100%, so we call it COP. But in the heat pump case, the efficiency is 400% compared to in the boiler case or burner case, the efficiency is about 80%. So heat pumps are generally very much more efficient than fossil fuel burning heat generating sources. And in this specific example, the heat pump is about 3 times more efficient than a gas boiler. So that is one of the huge advantages to heat pumps, is they're much more efficient at making and moving heat than a fossil fuel alternative. So these heat pumps can come in many different configurations, and I won't go through all of these, but the refrigerant that is used in that cycle, the compressor configuration, the piping configuration, the temperature at which you operate is all going to be dependent on the process in which you want to convert. So if you're looking at a heat pump, there's a ton of different options out there on the market right now, and you're going to have to work with a couple different vendors to figure out what your application is, what configuration works best for you, depending on your specific process requirements. Okay, so another quick question, what is the purpose of a heat pump? Multi-select, throw it into the chat. B, I see some Bs. I think the ones that I highlighted were B, we're moving that heat around, right? We're covering it from one area, and we're raising the temperature of that heat. I guess A is also correct. We are creating heat along the way, but that is not, we're creating some heat from already recovered source. So everyone got that mostly correct. Great. And then if you had to estimate a natural gas steam boiler efficiency or maybe a burner efficiency, if you were just doing some quick back of the envelope calculations, what would you guess? What percent efficiency? Okay, I see some 80% is what I think I put on here. And then I just see that Kai, you put 90 to 95% for a condensing boiler. I'm actually not sure off the top of my head of what a condensing boiler is, but I think I put 80%. But yes, thank you. It depends on the type of boiler. 80% is what I have here. Great. All right, so now I'm going to turn it over to Steve to talk about some of the applications for heat pumps right now.
So let's talk about where heat pumps are today. So in the US today, we have technology on the market that brings us pretty close to the boiling point of water. In Europe and Japan, heat pump technologies can make steam or superheated water. In the labs, those temperatures are pushed even further. So the US is a little behind other industrial nations, but there are products on the market and more continue to come on the market every day. So we're basically near steam temperatures, near boiling water temperatures. So where does this fit in the industrial sector today? This chart shows how much energy is consumed by several industries by temperature. And these 5 industries were the focus of the Department of Energy's Industrial Decarbonization Roadmap, published in late 2022. The first 2 bars are where heat pump technology fits, somewhere below 300 Fahrenheit or about 150 Celsius. If we total all these bars up, we get about 30% of the total pie, meaning that 30% of the industrial process heat load today could be served with heat pump technologies. If we dive into those categories further, what are we going to see? What specific processes in food and beverage space or the chemical industry can be served with low temperature heat pumps? Quite a few.
Real quick, Steve, we got an interesting question in the chat I thought you might want to answer. It's from Kai, and the question is, does near boiling temp in this context mean these don't work as well at higher elevations with different boiling points for water?
We're talking 100 Celsius, give or take. It doesn't, you can get stuff that goes, you can get heat pump products that go over that temperature up to like 120 Celsius from some manufacturers, but some manufacturers don't have products that go quite that hot. So yeah, it's not that tight to say, oh, sorry, because of your elevation, it doesn't work. And I don't think the heat pump really cares about your elevation. It's more about the temperature that you're trying to produce. And some of these heat pump systems that are producing hot water, the hot water might even be above 212 Fahrenheit. It might be pressurized hot water that's then moved around the system under pressure. I'm not sure I answered that very well. We can talk about that more.
Thanks, Steve. I think that was good.
Yeah. Some sites are not super excited about piecemeal heat pump replacements, like, oh, here's a small heat pump that serves this and another small heat pump that serves this load. They would prefer kind of a central plant solution that kind of replaces their existing boiler. As we talked before, lumber drying and some species of lumber do really well with heat pumps. There's great economics. There's no need for incentives. The moist, hot waste heat is a great heat source for the heat pump, and it can recycle that heat, raise the temperature, and put it right back in the same kiln. There are also a lot of dairies that use a type of a heat pump, a thermovapor compression, which is basically a Venturi type process where we take high pressure steam and we can turn what would normally be waste low pressure steam, we can turn it into a medium pressure steam and reuse it in the plant as a heat source. And that significantly reduces natural gas and steam consumption. And those are widely used in the cooking and concentrating industries today. Where is industrial heat pump deployment today? So I've been when I hear about a heat pump, I have a list, I put it on the list, and I try and keep track of it. This is my quick shot at what I see today. We know Leprino Foods has a couple operating heat pumps. They have another one that's about to start. There's a winery and a cheese plant that have heat pumps that have made the news. There's a lot of heat pumps that are being installed, but these are the ones that are actually operating right now that we can kind of confirm are operating. And I'm guessing maybe there are another 300 heat pumps in the US that are operating that I don't know about, including all the lumber drying heat pumps. So yeah, not huge numbers in the US. Europe and Japan, I'm guessing maybe there's 3,000 heat pumps in operation right now. Here are the questions we see corporate energy managers and businesses asking themselves about this technology. In the residential space, we see heat pumps going in everywhere. Heat pump sales passed natural gas furnace sales in 2022. And in the commercial space, there is a similar story. In the industrial space, a lot of these answers are sort of, sometimes, and maybe. There's not a resounding yes. And thus the widespread adoption of heat pumps is not really here yet. So let's talk about what are some of those maybes and what are the barriers to making that a yes. Nicholas has a 2 megawatt thermal heat pump beer pasteurization in Montreal. Yeah, that's going to be a great one. Of course, didn't make my list. It ain't running yet. Can't wait to see that one up. So first, let's talk temperature. The temperatures of the heat pumps on the market today are not quite enough to meet all of people's heating needs. We talked, heat pumps are going to be really good in the low temperature space, things below like 200 Celsius. They're never going to make 1,000-degree temperatures that are needed in some cement and steel production. Heat pumps aren't going to ever play in that space. Then a lot of people do want steam. And heat pumps can make steam in some situations. And high COPs require high temperature heat sources, which complicates the projects and can be expensive. The vendors, there are a handful of vendors that we'll go over. They have products available. Their sales are relatively slow, and support for customers is limited. If you want a vendor to jump in and lay things out for you and really help you pick a solution, that help might not be available right now. A lot of people in the industrial space don't want to be the first. They're risk averse. They want to be second or third to install the new technology. They want to see others in their industry do it first. They want to they want to see what their competitors are doing. These are some of the actors on the market today in the US. And in most cases, they're offering kind of custom designs based on the site specifics. A few vendors have packages where they kind of, instead of just having a wide open array of things that could be assembled, they're like, look, we'll assemble this with 3 options here and 3 options here, and you get a pick from those. And we're expecting to see more consolidation of the designs, more package type selections as time goes on. These are a couple companies that are offering steam system replacements. Atmos Zero is an air source heat pump that's capable of generating 90-pound steam. And the air source is the big selling point in that it doesn't have the complications of trying to integrate waste heat. Basically, you just bolt this to the ground and connect water and electricity to it and take the steam from it. You don't have to, the integration with your plant is not super complex. You don't have to route the waste heat to it. And it reduces the installation costs, but it hurts the COP because the air is not that warm, especially in the winter. And so the average COP expected from an Atmos Zero system is about 1.9 over the course of a year. Now that still beats an electrode boiler, which would have a COP of a little less than 1. So 1.9 or 2 is a lot better than 1. So we do expect to see these go in place of electrode boilers in a lot of places. They have a demo plant up and operating at the university, at Colorado State University today, and a brewery is going to have a second one of these up and operating in the first quarter of 2025. Skyven is another startup. They're using waste heat and multi-stage centrifugal fans to produce steam. It's a large steam system, about 50,000 pounds an hour of steam they want to make. And both of these companies have received DOE grants. Okay, question for you. An air source heat pump making steam might have an average COP of about, it's a memory check. Was the atmosphere zero COP? Yeah, 1.92. Yep, about 2. There you go. If we had a higher temperature waste heat stream, that could be 3 or 4. But if we want a simple system, we don't want to have to try and recover waste heat, we might get 2 from an air source heat pump. Very nice. Incentives and funding. So, oh, is this you, Regan?
I think so.
Gotcha.
Unless you want to do it.
No, you go ahead.
Okay. Great. So we're talking about right now barriers to heat pump adoption, which also translates to opportunities to heat pump adoption. So next up, we have incentives and funding. And one of the sticky points here is fuel switching. So utilities have a hard time figuring out how to handle incentives for these types of projects, since we're switching fuels. In many cases, we're going from natural gas to electricity, and that a lot of times isn't provided by the same utility. So one utility is losing a customer and the other is gaining more business. And so there's a hard time trying to figure out how we pay an incentive to get these projects completed. Which also then brings up the question of what is the baseline? If we can't incentivize fuel switching, what is a reasonable electric baseline for the electric utility? And is that truly the lower cost option for many of these projects? So that's one barrier that we need to get figured out. Another related to kind of the incentives and funding is if we don't have that funding available from the utility, there is funding available from the federal government, but those applications are oftentimes very complex, detailed, and pretty slow to get processed. So you have to have a grand plan, have that all ironed out, and then you have to be very patient in order to get these done. And it's often very difficult if you are a small business or if you only have one energy manager on site that has limited resources to kind of wade through all of this paperwork and get, kind of cross this red tape and get this all figured out. So that's one other complication. Right now, hopefully, a lot of these programs that are being rolled out can be a little bit more streamlined with a little bit more support so people can get the funding that they need to move these projects forward. And then the last thing here is sticker shock. So even if we do figure out how to get some funding assistance, these projects are oftentimes pretty expensive. It's a new technology, and integration and tie-in costs can be sometimes more expensive than the actual heat pump itself. So some businesses are just not willing to shell out the cash for these projects right now until we kind of sort out this funding or make it a little bit easier to move these projects forward. The available of funding or the lack thereof also ties into, most importantly, like the overall project economics. So regardless of what funding is available, heat pump projects have better economics where the price ratio of electric energy to gas energy is low. So this electric to gas price ratio is sometimes called the spark gap. So if your electricity is 10 times as expensive as gas, the economics for a heat pump are going to be pretty tough. Like that's probably not going to work out and save you money in the long term. If your electricity price is only twice as expensive as gas for equivalent units, then the economics might be pretty compelling. So some folks are also starting to look at this in their internal economic calculator tools, is they're starting to compare the spark gap using renewable renewable natural gas prices, since that's a little bit more expensive and might be more indicative of what future gas prices look like as we kind of move into this more taxed, more regulated environment to try to move to clean energy. So many times this simple spark gap ratio or spark gap can be the economic factor that like makes or breaks a project. It doesn't even have to do with the equipment costs. It's just this spark gap. One thing to consider though, when talking about spark gap is, you know, the numbers here are the current spark gap, but we also want to be factoring in that future spark gap. So some projections show electricity getting a little bit more expensive in the future, but eventually coming down as we figure out how to green the grid and we have an abundance of clean, cheap electricity. And additionally, natural gas prices might go up as there's more regulation or requirements to use renewable sources, and those just become more expensive. So the calculation for this spark gap is the electric cost over the gas cost in equivalent dollars per kilowatt hour. So in this example, if I'm paying 10 cents, laser pointer, if I'm paying 10 cents per kilowatt hour and $10 per MMBTU, I have a spark gap of about 2.9. Generally speaking, when we're looking at heat pump projects, if your spark gap is less than like 3 or 4, you probably have a favorable economic situation and a heat pump project might make sense for your facility. But again, it depends on a multitude of different factors, including the spark gap. One kind of scoping test, and this is a bit nuanced, but this is a concept we recently heard about, is to compare the spark gap to the efficiency ratio to get an idea of if the project will reduce operating costs. So in this example, I have my heat pump COP is 2. Maybe I'm looking at one of those Atmos Zero steam generating heat pumps. My gas boiler that I want to replace is 80% efficient. So if I divide 2 by 80%, I get an efficiency ratio of 2.5. And so how we can apply this number is if my spark gap is less than 2.5, this project will save utility costs. So I will be saving money on this project, just operating steady state as is, not including any capital costs. If my spark gap equals exactly 2.5, then I'm going to break even. And then if my spark gap is greater than 2.5, I'll be spending more on utilities with the heat pump compared to my natural gas baseline. So that's just kind of a great rule of thumb that you can apply moving forward, is if you're looking at a project and you kind of get those quotes or numbers back from a vendor, you can look at that COP, calculate your spark gap, and kind of look at what the utility cost breakdown will be. So in this example, we'll just kind of go through this together. Would this project result in an operating cost savings? So in this example, again, I have a heat pump or COP of 5. I have a boiler efficiency of 80%. We'll just assume that. And my spark gap is 6. So if I take my COP divided by my boiler efficiency to get that efficiency ratio, I get a 6.25, which is greater than my spark gap. So this project will have small utility cost savings. So again, that's a very quick way that you can kind of use the numbers that you have available to you from a vendor, from your utility, to calculate how possibly a heat pump would stack against the existing gas baseline. One other thing, and we kind of mentioned this before, is gas prices are very cheap right now, which are really not helping heat pump economics in the US. So if we take an average price of about $3 per MMBTU, that's equivalent to about paying 1 cent per kilowatt hour. So it's incredibly cheap gas. And if I'm paying 8 cents per kilowatt hour, that the project economics are really, really tough. So this is why one of the reasons that Europe is adopting heat pump technology faster than the US is gas is expensive and they really don't want to buy it from Russia. Natural gas prices can be volatile too, and that's a factor we and our customers should all be considering when we're evaluating a project. So looking at the renewable natural gas prices or trying to predict those gas prices in the future could help us move a heat pump project forward We also need to factor in the cost of regulation and carbon emissions. So there's a bunch of different factors that tie into this, but the spark gap and just gas prices in general are a very big driver of these projects.
All right, the last little section here, I want to talk about effort Cascade did and scoped a bunch of heat pump projects in the Pacific Northwest for Bonneville Power Administration. And I want to leave enough time at the end so we can have some open Q&A. But basically, we went and looked at 5 of the major load segments that are in BPA territory: pulp and paper, wood products, food processing, chemicals, and high tech, and tried to find heat pump projects in kind of representative heat pump projects in those industries. We basically went to the sites and talked with them about their heat loads and their heat sources. There's a very famous chart here in heat pump world, which helps you estimate the coefficient of performance. If you know a source temperature and a sink temperature, then you can have a reasonable estimate of what the COP is going to be, regardless of who makes that heat pump. And you might even use this yourselves. If you're, oh, here's a waste heat stream at such and such a temperature, and I need heat at a higher temperature. Is my COP going to be 1, or is it going to, is it going to be low? It's going to be down here at 2 if I have to raise the temperature of this heat like 100 Kelvin or 100 Celsius. You might only get a COP of 2. If I only have to raise the temperature of my heat 40 Kelvin or 40 Celsius, you might get a COP of 4.5. So with that known, and then the next assumption was, how much is a heat pump going to cost? Well, costing these things out is time consuming and the vendors get involved, and we kind of took a shortcut here and we used kind of an average of $400 a megawatt and $800, and we ended up using $600 a kilowatt per kilowatt of thermal heat delivered for our cost assumptions in this scoping study. I suspect that will be true eventually, but I would suspect right now you get full costs for a project that's probably going to be over $600 a kilowatt. We ended up identifying 22 industrial heat pump projects in high-tech chemical, pulp and paper, wood products, and food processing industries. We found good economics today in the high-tech and chemical projects. Pulp and paper and wood products had some iffy economics, paybacks closer to 5 years, which a lot of industrial customers won't do. The projects that we found in food processing didn't have acceptable economics. That's more to deal with the spark gap of the site than really the overall, because we have other projects in food processing that are good heat pump projects. So we'll just take a little bit of a detail. Here's the food pump. Here's the food and beverage project. See, their spark gap is 3.8, so their electricity is almost 4 times as expensive as their natural gas. But the heat pump COP was only going to be about 2.8 to make hot water for a blancher at 190 degrees from ammonia refrigeration waste heat. So that was only going to give a COP of about 2.8, and you can probably see a problem here, is that this isn't high enough to get us an operating cost savings. The next project was at a pulp and paper using 90-degree wastewater as the heat source to produce 140-degree processed hot water, 140-degree Fahrenheit. Their spark gap was 2.5, but the heat pump COP was 5.8. So we're going to save some money here. We're going to save $70,000 a year. And the payback for this project after some utility incentives was going to be about 13 years. So, I mean, not a lot of companies will bite off a 13-year payback project unless there's other reasons they want to do this, decarbonization goals or something like that. So some operating cost savings, but an expensive project and not a super fast payback there. This third project we'll talk about is at a high-tech plant that needs to make some hot water. And they're going to make that basically from cold water. Now, their cold water isn't that cold, but they have a cold water load that they need to maintain at 80, and they need to maintain this process hot water at 175. Well, that gives us a COP of about 3.3. And with a spark gap of 2, this is a healthy amount of savings here, $160,000 a year. And after incentives, that was about a 3.1 year payback. And Nicholas, the large Washington customers that are subject to that carbon pricing, this economics does include that, and that actually helped in a couple of these. Is that incorrect, Regan? My understanding is that did impact a couple of these sites. I don't think it impacts any of the sites that we're talking about that I'm highlighting here, but some of the sites some of the 22 heat pumps that we identified, the economics were impacted by that, and it helped them a little. And Glenn's asking, what is the carbon price? I can just speak to this vaguely, because I'm not super in tune with this, but in the state of Washington, some of the largest carbon dioxide emitters pay a price for carbon emissions, and by doing this project, they reduce their carbon emissions, and so this helps them avoid some of that price penalty. So if someone else is more familiar with that, feel free to raise your hand. We'll unmute your mic and you can speak. And the last project I'll focus on here before we open up was a chemical manufacturing plant. And they basically were just going to install an air source heat pump, simple installation, and make 125-degree water. So not super hot water. And their spark gap is very low, which means this is going to be favorable, likely to be favorable. So 1.2 spark gap, the heat pump COP is going to be about 2.5, save about $13,000 a year. And so after some utility incentives, this project was going to have a payback of 2.1 years. So it's just some of the quick paybacks is if you have electric resistance heat, that's going to have a COP of 1 at the most. So if you move to even an air source heat pump that's got a COP of 2 or 3, depending on the temperature, then you're going to crush this electric resistance heat. And we also found places where they weren't doing heat recovery. And so before you install a heat pump, you want to do all the heat recovery that you can find. And then the spark gap will kill a project faster than anything. So if the spark gap is not favorable, you can, and the economics are your motivating factor, then you can kind of stop searching for heat pumps. Another interesting thing was we did look at a couple wood products manufacturers that were burning hog fuel. Well, hog fuel is considered a biofuel and carbon neutral. So actually going from a carbon neutral source to electricity would not have CO2 savings. It actually would increase CO2 emissions, at least until the grid was 100% green. And then, you want to use utility incentives. Yeah, it was able to reduce reduce the heat pump simple payback by 50%, and a large pulp and paper mill that was paying that is subject to that carbon tax. And so, some of these sites had corporate energy goals and corporate decarbonization goals, and some didn't. Yeah, so the spark gap is very important to determine whether a project is going to have decent economics. Heat recovery could come first. We did hear from customers, man, it would sure be great if I didn't have to do 6 heat pumps, if I could just put in a single steam generating heat pump plant. Of course, heat pump's going to beat an electric boiler and renewable natural gas, which will be quite expensive. And with that, we have 6 minutes left. Let's answer some of these questions. What refrigerant do industrial heat pumps use that you've looked at? Some use ammonia. Some use some halocarbon, some HFOs, the hydrofluoroolefins, the R1234ZDE. Those are the ones we've run into most often, are the just ammonia and then the halocarbons. No, not the halocarbons. The HFOs, the hydrofluoroolefins, seem to be the popular ones right now.
Steve, there's another one that came up earlier in the session that I thought you could answer, which asked, could air source heat pump making steam use ground source heat pump instead to get a higher COP, like building heat pumps can do? So ground source for
Maybe
industrial.
If you can get enough heat out of the ground. The problem is some of these industrial processes need a lot of heat all year long, and you might not be able, there might not be that much heat in your ground that you can, you might pump all that heat out of your ground in the first 3 days of operation, and now your ground's just getting cooler and cooler and cooler, and your performance gets worse and worse and worse. So that's the cost of putting in that ground source. If you got to bury 6 miles of tubing underground, or do something similar to that, it can be expensive.
Yeah, and I know that there are some technologies that are improving the deep drill availability and the economics of that. Here's another question from James Cantwell. What are your thoughts on adjusting the temperature lift of a heat pump project to achieve an acceptable COP in relation to spark gap? For example, supplementing the additional heating demands with alternative sources rather than achieving the complete heat demand via heat pump. So adding supplemental heat from other sources to achieve that spark gap.
So you're saying let's say we just do half of the heating with a heat pump, and then we do the other half with natural gas?
I suspect that's what they might be getting at, is some mixture of the two. Yeah.
My gut feeling is that won't really make the economics any better. You have a half solution and you still have an expensive project. You might just end up with the same answer.
I'll speak to one example of this that I've seen, Steve, that I'm interested in your thoughts on. And this was the application of an industrial heat pump to really offset boiler heating. And so they didn't get rid of their boiler, but they did the primary lift from whatever, 55 degrees to like 130 with a heat pump, that using heat recovered from a refrigeration system. And then they finished that last 70 degrees with a boiler.
I mean, that's just heat recovery. You're just heating boiler feed water.
Yeah.
Yeah, I mean, I guess I could see that if you had a heat pump there that can give you good economics into your boiler feed water, sure. So I guess I could see that. I guess I could see that working. The heat pump Doug and I toured, they actually needed like 80 Celsius water, but the heat pumps available when they were building this plant only made 70 Celsius water. So they made the 70 Celsius water with the heat pump, and then did the last 10 degrees of heating with another heat source. But that wasn't because they wanted to. That's because the heat pumps available at that time couldn't get all the way to the 80 Celsius. I'm sure they would have preferred to have just had the heat pumps do all the work and simplify their installation.
Yeah, I see some great comments. Any other? Oh, here we go. Here's another one. This is from Nicholas here. In the same vein, something else to consider is that most utilities will offer a lower price for electricity if the load is flexible. So swinging to a standby boiler in peak periods may improve economics.
Yeah, that could be nice. Industrial processes do not like to be told you can't run today because the electricity is too expensive. They want to run these facilities every single day. But yeah, if there's an opportunity to keep your gas boiler and then fall back on the gas boiler during those peak periods in exchange for a lower electric price, then sweet, let's do that.
Any other questions?
But we actually have, I don't know that we have specifics where the utilities have offered a lower price because of the heat pump project. Now they may have a different interruptible tariff, but that's kind of a separate question than the heat pump project, kind of independent of the heat pump question. If you want to go on a more of an interruptible rate, that's still available, and you could work that in with your heat pump project. Well, Kai, I think long term we hope that long term we hope that natural gas is not burned, and the whole economy transforms away from that. But that's a concern that natural gas wouldn't be available. That's probably 30 or 40 years into the future. Be my estimate. O&M and technical network for heat pumps. How do you feel this is developing? Do you see local refrigeration and service contractors become engaged in the heat pump area? Not really. A lot of the local contractors don't know much about heat pumps. The market's just young. There's not a lot of work going on, and they will learn as they get projects. And when you don't have projects going in, yeah, they're like the customers. They want to do the work when it's there and it's paying them money. They don't want to invest a bunch of time and resources in a young market. Yeah, I imagine the natural gas network and supply will be out there and reliable. Hopefully our use of it falls, but that is a long-term concern. And even like for cars, I mean, how do we fuel the remaining gas cars in 30 years when 98% of the cars are electric? I mean, somebody's got to think about that. We have to have some gas stations that still work for those cars. That's a little above my pay grade.
Great. I think we've had some really great engagement, and we're just past the hour here. So I want to be respectful and mindful of people's time. We can stay on for maybe just a few more minutes if folks want to. But otherwise, I'd like to thank Steve and Regan for really providing a great talk and educating us on industrial heat pumps today. Okay.
Thanks, everybody.
Thanks, everyone. Without further ado, have a wonderful rest of your day, and thank you for joining us.